In this video, we're going to look at 3 different types of graphs used to display quantitative data, and then we'll look at a 4th one in another future video. Here's some data that represent the scores of 100 golfers who played in the Save the Squirrels charity golf tournament at Bunkers and Divots Country Club last Saturday. When we look at the data, the way it's displayed, it really doesn't tell us much of anything. We need to organize it so the data will tell us a story. So we're going to start by putting it into a dot plot. A dot plot uses a dot to represent each data value, and the number of dots in a stack tell us how many are in each how many of each score there are. The dot plot is best if you have integer values and fairly small data sets with a small range of values. Now notice how much more we know about the golf tournament than we did before. Now we know that the average score is somewhere around 96 to 98 points. We also know we have a couple really bad golfers who scored very high number of strokes up here, and a few very good golfers down here, but that the majority of our golfers are pretty much average, not PGA, professional quality golfers. We also know there's a fairly wide range of scores here. Now, another way to display this data is in a stem and leaf plot or a stemplot. Now once again, a stemplot is best for small data sets with fairly nice numbers. If you have a number that's like 1,586, you need to round it to 2 to 3 significant digits because we want to divide them into what's called a stem and a leaf. And the leaf is always the 1's digit. The stem is usually a 1 or 2 digit number. The key tells us what the stem and leaf represent. So when we see 11, 6, that means that's 116 strokes, 11 being the 10's place and the 6 being the 1's place. So this number right here, 78, represents the score of 78. And this right here, the 12, 6 is 126. That represents the score up here. And there's the 123. So right here we have 3 scores, 81, 81, and 83. Now, when you draw a stem and leaf plot or stem plot, you're going to have the stems here, a vertical line separating the stems from the leaves, and a key explaining with context what the numbers mean. These numbers over here to the left are a special column of numbers that are added in some computer programs. And I'll just briefly explain to you what they mean, but you do not need to put these on your stem and leaf plots. What these are telling you is something called cumulative frequency. This tells me in the first row there's 1 golf score. In the second row and the first row put together there are 4 because there's 1 and then another 3. In the first, second, and third row put together there are 16 scores because there's another 12 scores in this row, and you keep doing that. Then you also count from the bottom. Here's 1 score. In the bottom 2 rows there's 2 scores. In the bottom 3 rows there's 4 scores, and so forth. When you get to the middle, where the middle is, so that there's half scores on one side and half the other, that means that middle number, which is called the median, is somewhere in this row, and this row has 20 scores in it. So that's what these numbers are telling you. Like I said, you do not have to write them. Also, I want you to notice something called the split stems. Notice that we don't just have 80 in one, this represents 80 in one row. We have 2 rows with 80. This is 81, 81, 83, and then we have 85, 85, 86, and so forth. When you have split stems, you put the lower digits, the lower 5 digits from 0 to 4 in one row, and then the upper 5 digits from 5 to 9 in the next row. So that spreads your data out a little bit so you can see the distribution a little bit more clearly. I want to show you an example in the book of what's called a back-to-back stem and leaf plot, and this has a couple features that I want you to notice. Number 1, the stems are in the middle, and you count the leaves out to the right for the males and out to the left for the females. So this, for example, would be a male with 10 pairs of shoes and a female with 13 pairs of shoes. Here's a male with 35 pairs of shoes, a female with 38 pairs of shoes. Something else I want you to notice is that there are gaps. So for example, here there are no data values at all in the lower 40s. either for males or females, but I don't want to leave that out. I want to show that there's a gap there between this value of 38, no values from 40 to 44, and then there's a value of 49. So that's important to show gaps in the data. This is a really good way to compare two data sets because this makes it really clear that males tend to have a lot fewer pairs of shoes than females, which is no big surprise. It also shows us outliers in the data. Let's go back and look at our third type of graph. The third type of graph, which is really great for any large or messy set of data, is called a histogram. In a histogram, rather than having a stack of individual data values, we have what's called a bin, which is like a container. You may have heard of a storage bin, kind of a container that holds the data. So we divide the scores into groups, and this is our scale on the bottom here. So our scale here goes from 77.5 to 127.5, and it's divided into bins of equal width. Each bin has a width of 5. So this one goes from 77.5 to 82.5, from 82.5 to 87.5. The bars are right next to each other. We don't leave gaps in between like we do with a categorical bar graph. The only time there's a gap is if there's nothing in that bin. It's a bin that has no height to it. The height of the bin tells you how many data values, individual data values, are in that bin. So here, the frequency of 15 tells me there's 15 golf scores that are between 107.5 and 112.5, which are the edges of this bin. Now, how do you know how many bins to make, how wide to make them? So rule of thumb is you want to use nice numbers. So I say nice, like whole numbers, nice numbers for the bin width. You don't want your bin to be like 4.2 units wide. And we often want to use whole numbers for the bin edges. Sometimes you use like the 0.5s. The reason they did this is so that if you had a golf score of 77 or a golf score of 82, that it wouldn't land on the edge of the bin, it would land in the middle of the bin. And so sometimes that's done, but typically it's kind of nice to have bin widths that go like from 80 to 85, 85 to 90, 90 to 95. Sometimes those are a little easier to read. So I'm going to show you an example on the calculator of one like that. So on the calculator, this is a histogram of the number of Fruit Loops. Well, I put a bunch of Fruit Loops in a bottle, and I said, how many do you think are in there? And these are the guesses that students made. So this is relative frequency. I think I'm going to change this to frequency, which is kind of nice. Plot properties, histogram properties, we're going to change this to frequency. Okay, so this tells me that one student guessed from between 50 and 100. Another student guessed 5 students guessed between 100 and 150. 3 students guessed between 150 and 200, and so forth. But what if a student here in this particular bar, there were 7 points, what if a student guessed exactly 250 or exactly 300? Would it fall in that bar, or would it fall in the bar to the side? So if you look at the way this is written, there's a square bracket around the 250 and a curved bracket around the 300. That tells me that the 250 is contained in this bin. The 300 is not contained into this bin. It goes all the way up to 300, and then if someone guessed 300, it would actually be in this bin to the right. So if a data value lands on the right-hand edge, it goes to the next bin. If it lands on the left-hand edge, it stays in that bin. That is the particular default way that our calculator does it. Every statistics technology has its own default way of handling that, but this is pretty typical. I don't know if there's anything else. I don't think there's really anything else I need to say about that, just to show you another way to do this. And all programs have different ways of adjusting the bin width. Typically, we want to have between 8 and 12 bars in because if you have too many bars, so let me just show you kind of, if I make the bars smaller, too many bars, it's kind of like it's hard to read. You can't really tell what the data is telling you. If you make too few bars, and I can adjust this so I can see this better. If you make too few bars, then it doesn't really tell you enough about the variety of guesses, and it doesn't show you that there's an outlier, because we had an outlier before that was a little more clear. When we had fewer bins, we could see that there was an outlier. So you have to adjust bin sizes so that the data tells you kind of what you need to see. You need to be able to see outliers. You need to be able to see few enough bins so that you get the big picture, but enough bins so that you can see outliers and gaps that are important. So that's kind of the rule of thumb.